So in this video, we're going to talk about waves in matter. Basically because everything that we've done so far has been in vacuum, and the real interesting stuff with electromagnetic radiation happens when it's going between media, and you can start to see what happens when you have a transition between two different media. So what we'll have to do is we're going to have to dust off the Maxwell's equations for materials, which is del dot D is equal to the free uh, charge density. The curl of E is still equal to minus dB dt. Del dot B still vanishes, and the curl of the H field is related to the free currents and the time derivative of the displacement field. And here, as we had in the past, D is equal to epsilon naught E plus the polarization field, and H is equal to 1 over mu 0 B minus the magnetization field. So we're going to investigate what happens when we set rho f to be 0 and jf to be 0. This is just like saying that there's no free currents and free charges anywhere in the region. So this should be very similar to what we ended up with when we worked with the wave equation in vacuum. So we'll start this, and then we'll see that we're going to run into a slight problem. So we'll take the curl of the electric field equation that we had before, and that's going to give us the negative time derivative of the curl of the magnetic field as we had before. And then we'll end up with the gradient of the divergence of the electric field as we had before, minus the Laplacian of the electric field, still equal to the time derivative of the curl of the magnetic field as we had before. Now, the only issue here is that our equation that describes what the divergence associated with sort of an electric-y kind of field thing is del dot D. So what this tells us is that when we have no free charges, del dot D goes to 0. That does not necessarily imply that del dot E goes to 0, because it will depend on what happens to del dot P, the polarization. Right? These two could collude together. And so we have a problem in that we can't really reduce this equation anymore without making some additional simplifying assumptions. So we'll go ahead and do that. Those simplifying assumptions are going to be, first, that the material is linearly responsive. So this is the kind of material that we've worked with in the past. This is the kind that we spent a bunch of time on last semester. And that is that the D field is related to the electric field through epsilon, and the H field is related to the magnetic field through mu. The other assumption that we're going to make is that both epsilon and mu are constants for any given material. They're homogeneous constants in that, in principle, epsilon can depend on position and mu can depend on position in interesting and exotic materials. And we are going to say that that is not the case, that instead we just have these constants. They're very, very simple constants. They're ones that we can deal with in a very straightforward manner. And so what these two simplifying assumptions allow us to do is they say, well, now if we consider the divergence of the electric field, we're going to be taking the divergence of the D field divided by a constant epsilon, and both of those things vanish. So we get rid of the issue that we had before. The other thing that we're going to say is if we take the curl of the magnetic field, the B field, that's simply equal to mu times the curl of the H field, because mu is a constant. So everything behaves just like it did before in a relatively simple way, and we can sort of track all of this stuff through. But at the end of the day, what we are going to end up with as an equation, for example, for E, will be that the Laplacian of E is going to be equal to mu epsilon times the time derivative of E. This is the wave equation for E in material. And the only thing that's changed about it is what's going on right here, namely that waves move at a different speed in that material. So let's unpack that just for a moment. So we'll rewrite this equation just for the sake of keeping track of what we're doing. And so this is the wave equation in material. And what we find is that waves move with a speed equal to mu epsilon 1 over the square root of that, instead of what we had before in vacuum was that c was equal to mu naught epsilon naught 1 over square root there, right? So this is actually really interesting because the only thing that's different about this situation is really the speeds. All of our old results still apply. Um, you know, everything that we've done with plane waves still applies. B is still going to be perpendicular to E, and both are perpendicular to the k vector, and B is still related to the electric field magnitude by the speed that it travels with. You know, all of these results that we had for plane waves still work. Everything still works. It's just now that we have a modified speed. Now, there's a couple of small footnotes that I want to make about this, things that are kind of just important to keep track of. One is that epsilon is always greater than epsilon 0. That is just something that it is a principle of nature. So the other one is that there's actually two kinds of materials that we might have to deal with. So mu can be greater than mu 0, or it can be less than mu 0, depending on whether it's paramagnetic or diamagnetic material. But typically, it's the case that where epsilon can be very different from epsilon 0, it is typically the case that mu is about the same size as mu 0. So it is very, very common for us to just make this replacement and just keep track of what's going on with this dielectric constant. So the details of that are due to sort of the material's ability to magnetize, essentially. Now, the last little note that I would like to make about this has to do with this thing that we'll begin to define as the index of refraction. So that speed v that we're keeping track of, which is mu epsilon, oops, not epsilon 0, sorry about that. It is 1 over the square root of mu epsilon. We can look at how big of a factor there is associated with that change by basically introducing this thing that we'll call n and relating that to mu naught epsilon naught, like this, which tells us basically the speed of light divided by some coefficient. This coefficient is what we will call the index of refraction that's going to come back. So it's basically how much does this differ from vacuum. So in this case, n will always be greater than 1. So what we've done in this video is derive essentially the wave equation for materials and shown some of the results that come out of it.